Okay, so here's some videos. Here's the first of, looks like it's going to be three because I have three examples, relatively long examples before exam 2. This is really sort of a review of various problems, but I mean kind of the culmination of the different topics that we've covered since exam 1. And those are safety factors, stress concentration factors, maximum shear stress theory, distortion energy theory, brittle Coulomb-Moore, and fraction mechanics. So we're going to do a couple of examples. I think example 2 is going to be a stress concentration, which is almost too similar to the homework, but it's different, not identical. So when we get to that, but this video is going to be covering this problem right here, which is also a problem that, as I recall, Dr. Ghosh, who would typically teach this class before I came to the University of Hartford, he would pick this class quite often. And I think there's going to be a little bit of differences in here, I think, from, I have a couple of things crossed out in the scan of the thing that I made here. So one thing, the shaft is made from 3 or 4 stainless steel, and we want to find the safety factors based on the maximum shear stress theory and distortion energy theory, and perhaps we want to actually redesign it if it doesn't meet some standard. So we'll make it kind of closer to what real life would be. So the shaft starts out as 30 millimeters and is simply supported at the ends by bearings at A and E. And pulley C receives power from a motor right here, and with the belt tensions that you see of 300 newtons and 2,000 newtons, right? So, and the motors, blah, blah, blah. The power is transmitted through the shaft and delivered to pulleys B and C. So there's 3 pulleys. That's something we haven't done yet. And pulley D, the belt tensions on the loose side is 20% of the tight side. And the 3 pulleys are keyed to the shaft. So we might have some stress concentrations put into there. And pulley C is of a diameter of 100 millimeters. And pulleys B and D are 200 millimeters. The pulley on belt B is at 45 degrees right there, as you kind of see right there, right? It's kind of going in. It's not up and down or left and right kind of thing. Each pulley is held in place by a tapered pin. See, there you go. Why would I say to use the keyed to the shaft if I had a tapered pin? That's why I crossed that out, apparently. Okay, so duh. So which one is it? Is it going to be keyed to the shaft, or is it through a tapered pin? I don't know. Let me see what I did in my problem here. Did I do stress concentration with a tapered pin, or did I do it with a, I did it with a tapered pin. Interesting. Instead of a keyway. I think I would prefer to do it with a keyway. But let's just get this thing going, and let's see. So I'm going to close out of this. Let's see. Do I have anything next to this though? Do I have anything in the next slide? I do have some information on Keyways. Maybe we ought to talk about those before I start the problem. Yeah, these are excerpts from a copy of Peterson. I'm not sure it's the particular Peterson had several books, I think. But anyway, it gives you these uses R over D, where so the radius R, if I'm correct, looks like it's going to be at the bottom of the keyway. That's usually a really tight. I don't even know if some of them even have a radius right there. They must have some kind of radius. But anyway, this is, but it's kind of interesting if you take a look at the typical R over D. This is something like 2.1 right there, right? And that's for the bending mode. Yeah, you see the M's right there for the bending mode. And then this one is for the torsion, I believe. And if you look at that, I think you get near this 3.1 right here. And those two values, I think 3.1 3.0 actually, and maybe a 2.1, but actually I think it's 2.7. Those things are given in Shigley as examples. Just figured I'd mention that. But anyway, there's also had some pictures of the end mill versus the end mill is A, so you can kind of see that the mill stops, right? They take the mill thing and they come down into the shaft, and then they go straight along, and then they pick it back up. Whereas the sled runner, that's where they kind of like slowly lift the tool up as they're coming out of the keyway right there. So that's what they mean by the difference between those keys. All right, so I'm going to rewrite the problem out because I don't have it, the notes here in front of me, so I'm going to have to pull this over to the side. I'm really not very organized right now, so I apologize for being so confusing, but I just have to get through it. All right, so let's see. I'll draw out my problem. I like to redraw out the problem. It makes me think of the problem as I'm drawing it out. And here's our other pulley. And there's the end of the shaft right there. And then it's going to a bearing, which in this case they make it look kind of funny, and they just have the bearing kind of look like a little pinned kind of joint right there. A little weird. All right, so the shaft continues up to there and has a pin. And let's see, this guy is the one that's weird. It's going at a 45-degree angle. Didn't quite make those two parallel to each other. And I think it's actually, the thing that's causing the focus problem is the clip on the, yeah, maybe that's it. Okay, let's see, boom, here we got this guy, and this one's coming down. And he's 100 newtons, he's 900 newtons, and he's 300 newtons, and he's 2,000 newtons. The distances are given in a table. Let's see, first off, this is Y and Z, and that's X, and they decided, I hate they call this, I don't like to call it T. T is a torque, personally. That's my opinion. But this was A, B, C, D, and then E right there. And the distances, like I said, were given in a table, but I got distracted. So these are 100. Everything's in millimeters. Let's see. It's not a very good place to put this. I guess I will go and do what they did. AB was 100 millimeters. BC is 250 millimeters. CD is 250 millimeters. All right, so I guess that's 100 there, 250, 250. And then right here is, oh, it's symmetric. Look at that, DE, 100 millimeters. The diameter of B is 200 millimeters. The diameter of C is 100 millimeters. And the diameter of D is going to be 200 millimeters. And the shaft diameter, preliminary shaft diameter, is 30 millimeters. And anything else we want to know here? I don't think so, except that the looser is 20% of the belt on D. These are looser from each other, but you can't quite tell from this which is going to be the tight and the loose. I guess you probably could. Maybe we could just look down the end of this right here. All right, so I'm going to make this one slightly smaller than that one, even though they have the same diameters. Oops, didn't make the concentric. And then C, I'll make it this way right there. So there's going to be C, and this is going to be D right there, right? I didn't quite make those a very good drawing of this. So this is 100 newtons, 900 newtons, right? And this is 300 newtons and 2,000 newtons. So we could just apply some logic here to see which is going to be more and which is going to be less, even though in terms of the tension, even though we're not sure. We do say we are told that this is where the power is coming at input, and both B and D are power out, right? So we're going to imagine this guy is driving the main driver of the thing, and it's causing clockwise rotation. So here's counterclockwise rotation, right? So it takes out some of it. So you expect that this is also going to be counterclockwise rotation, so that FT2 must be bigger than FT1, right? So that FT1 is equal to the 0.2 of FT2. So FT2 is larger than FT1, so that means that FT1 is 20% of FT2. So if we take the sum of the moments and take it about the x-axis right here, I'm going to go ahead and take these as differences right here. So I'm going to say 2,000 minus, and this is clockwise, 300 times its diameter, which is the, well, by the radius really, but 200 divided by 2. Yeah, everybody's going to be divided by 2, and everything's going to be in millimeters, so it's all just going to cancel out to be able to find out what the FT2 is what we're going to try to solve for first. Okay, so that's this guy, this C right here. Let's go to A, and now this guy is counterclockwise, so it's 900 minus 100, and that's going to be I just said the wrong number over here, by the way. That's always infuriating. Sorry. This is on C right here. This is the small guy right there. So he's the small one. So that should be 100. And then this is supposed to be 200 over 2. Right. So I eventually got it right. And then this one is going to be also counterclockwise, so plus, and we end up with FT2 minus 0.2 FT2, and I ran out of space here on my page. Poor planning. This is also a 200 divided by 2, and that whole thing equals 0. Okay, so we can find out our FT2. I actually have the solution here, so I don't actually have to spend the time writing down, doing the calculator thing here. You could prove. I mean, for some of this, I might end up doing it, but I made a nice little mess right in there. Okay, so I'm going to say that that tension is. Oh, I did it in a couple. I did it in a totally different way. I don't like how I did it. So I'm going to write down. I am going to use my calculator for some of this. So we're going to go 2,000 minus 300, boom, times our 50. Exciting, all right? And then we're going to subtract out this right here. So 900 minus 100, so that's 800, times our 100, boom. We're going to subtract that out. Yeah. And what's going to be left, we're going to divide what's left by that, by 100. Boom. But we're going to divide it by 0.8. And I hope I got the right thing. Let's see. Did I get the right thing? I'm wondering. Where'd you go? I did not. Let me try it again. Boom, baby. 2,000 minus 300. Did I get that right? Yeah, I think I did. Times 50. Great. All right, and then 900 minus 100, duh, is 800, and times 100. Boom. And I am subtracting. Boom. All right. Now I want to divide by 100. If I have the dimensions correct. Yes. Divide there, sure. Now we'll divide by 0.8. Yes, I got 62.5, which is what I expected. That's not a lot. That's a very small amount, right? So my FT1 is just 0.2 times that, 62.5. I did not come up with this problem. I think I came up with the trying to make a stress concentration out of it. But I'm looking at the thing again going, you know, I should have just picked a different problem, but that's all right. There's not that many problems to pick from where I didn't have it back then. All right, so I need to get the torques, and now I know these tensions. I need to get the torque right here and the torque right there. Of course, there's no torque in there, and there's no torque in there. But I don't know which one is going to be more necessarily from the beginning. I would actually probably guess this one's going to be the more. So I can do this in a number of ways. I think I'm going to take the easy way. I'm going to take and cut. First, I'm going to cut the shaft. Boom, boom, boom. And I'm going to cut it right here, and then just look at that guy. All right, so he is in that direction and that direction, and 900 newtons and 100 newtons, and therefore the reaction inside the T, and I'm going to call this BC because it's between B and C. And if I was going to be correct, by the way, I would also put in reactions right here, R, Y, and R, X. I don't know what those are, but I don't care. But there should be some forces in there just to balance this thing out. Summation of moments about the X, and what we're going to end up finding is, once again, I'm going to go and cheat, and I'm going to say 900 minus 100, and the radius of this thing is what we're really going to care about, and that's 200 is the radius divided by 2, and maybe I want to make it a 0.2 because I want things in Newton meters, right? And these are newtons and this is millimeters, so I turn it into 0.2. And then that's going to be minus my TBC equals 0. So TBC should be equal to, well, that's easy enough, right? Should that be 800 times 0.1 or 80, right? So that would be what it should be 80 Newton meters, maybe. Let me see. You get to see my sleeve here. 80. Where's my torques? Maybe I did it later. I must have done it later. Yeah, this is not a very well organized set of notes, by the way. I'm being critical of myself right here. Yeah, I got 80. All right, so I could just trust it and not even bother to look at the thing anymore. All right, so let me do the other torque that I'm going to need is this one. I'm just going to use this pulley by itself and cut it right there, even though I'm going to look down the same axis and onto the thing. And these are the ones that I just ended up getting, and they're going to be, let's see, T1 was 12.5 newtons, and this is 62.5 newtons. So this is not going to be a whole lot. All right, so this is going counterclockwise. So this T, and we're going to call this CD, is coming that direction. And if we were going to be technically correct, we would say that there's a reaction in that direction. So the sum of the moments about the x-axis right there. We're going to go 62.5 minus 12.5, and this is well, this is the 200, this is a 0.2 radius onto this thing, and then and that's minus TCD equals 0, so TCD is going to be, this is 50 times 0.1, so that's going to be a very small 5, right? 5 Newton meters, is that correct? 0.1 times 50, sure, right? So there you go, there's your torques. Something I might also need to get when I'm going to go get my reaction forces at the bearings, I need to get like the vertical and horizontal components of this piece right here at being 45. They're going to be equal to each other, but you see that we have 1,000, right, total going in that direction. So that means that we're going to have, so like 1,000 comes in that direction. Therefore, in the horizontal direction, there's going to be 707.1, right, newtons, and 707.1 newtons coming in that direction. I mean, in terms of I'm total on there. So I just wanted to point that out here before I go to this portion of the thing. I'm gonna get rid of my clipboard here. It's nice to have a clipboard, but until it starts, the clippy thing starts getting in the way. So let's see. We'll draw this 2 views out here, maybe in. So in the X and Y, we have our and I guess I'll draw the whole thing out. I don't need to make. We'll just make it all of us. There we go. Short, big, short, big, short. All right. I guess I feel as though I want to erase that line. All right, so looking at this, looks to me like we have, if this is X and this is Y, this is 707.1 newtons. This one we can't see, and this is the combination of those two before, which is 62.5 and 12.5. So what's that? 65? No, 75. 85? No. All right, this is stupid. 62.5 and 12.5. There is 75, man. All right, so 75 down right here. So we got 75. It's really not going to make much of a difference, is it? Seems to me we should have changed some of these values up in there to make this a more legitimate problem. But that's okay. It's just an exercise. And then in the other direction, let's see. We're actually looking, if we're looking down on this thing, sorry, Z is in this direction. That's Z is in that direction. And X is in that direction. Therefore, this must be coming out that direction right there, right? Boom, with the same 707.1 newtons. And now this one is going to be going 2,300. This right here is going to dominate everything. We already know, and then we're not going to see anything onto there. So let's put our reactions onto this. Our reaction is going to be downwards. I think it's going to be downwards on both of these, even though that's 75 there. It hardly matters at all compared to this thing. So I'm going to call this RAY, and now this one has to be REY. Come on. And then the same thing on here. Well, I don't know about this one for sure. I think maybe I'm going to guess our Z is right there, and I'm going to guess this is, I know this one for sure, R. You know, I really think that they both should be coming up. So I'm going to guess they're both up, because this one's in the middle, right? And although this one's close to that right there, I think this one is going to go that direction. So this is our res right here. And just making our shear moment diagram underneath this. I'll pre-make my lines, even though I don't know if I'll be giving them enough space, but we'll see. And the distances here, I should probably like write this in. These are 100, 250, 250, and 100. 100, 250, 250, and 100, I think. Yeah, based on that little table thing that we had in the beginning. And okay, so I want to look at some of my values before, just to avoid making stupid mistakes or showing you my stupid mistakes. Summation of moments about A equals 0. So we will say 707.1. And we could go ahead and use millimeters. It's not going to hurt anything. 100, and then this one is negative 75, and 250, so that's 600, right? And then this one is going to be going clockwise, R-E-Y, and it's now it's going to be 700. So R-E-Y 707.1 is times 100, 75 times 600, and we're going to subtract that out and then divide by 700. And I get, this is 36, doesn't seem like a lot, 36.73, yeah, newtons. And he's coming down. And then I do the sum of the forces in the y direction is up. I forgot to tell that. And I'm predicting he's down, pretty sure he's down. Plus my 707.1, and then minus my 75, and then minus my 36.73 equals 0, and I get an RAY, whoops, I'm sorry, I got it out of the thing. 707.1, whoops, I hit the button twice. Darn you, 7.1, 75 minus 36.73 minus, and I get 595.4 newtons, and sure enough, he is coming downwards. Sum of the moments about A equals 0. And I get a, also here, 707.1 times 100, because he is going that counterclockwise. But now I have a minus 2,300 times my 350. And now I have to have a positive REZ times 700. REZ, it looks like RE7. Equals 0. So I got REZ, Z, 707.1 times 100, and then 2300 times 350 times minus, and then divide by 700, and we get a reaction, a pretty large reaction, of 1,049 newtons, and as predicted, it's up. All right, and then let's see, I want to go to some of the forces in the z direction equals 0. Z is positive that way, and I'm predicting a negative RAZ. I don't know why I'm predicting it's not a negative, but I am. No, I know why I'm predicting it. Then we have negative 707.1, and then we're going to have a positive 2300 coming down, and then we're going to have a minus 1049 equals 0. So RAZ is going to be 543.9 newtons, predicting that way. Oh, there you go. So when we do our shear diagram, right? In our shear diagram, we got a lame. No, it's not a lame. It's a pretty good amount. Boom, come up this amount, and then we're going to have 707 upwards. So let me write this down. This is a negative 595.4. These are newtons. These are going to be Newton meters. And then we come up 707. That means we end up with that makes it 111.7. And that's the same all the way through, so it's 111.7 newtons. And then 75. So we don't actually even cross all the way down. And that ends up being 36.73 right there. So what this looks like, I didn't plan this out well. I could have, because I have it look right here in front of me. But let me point that guy right there. There's a moment. And then we have this slope like this right here. But then this is a different slope. Now they look the same though, don't they? Boom, 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 boom. So we want to find out what all the moments are at each of those locations, because we don't know where the maximum is necessarily 100%. So we take our 595.4 and multiply it by our 0.1, and we are left with a negative 59.54. All right. Then take 111.7, multiply it by 0.25. But it's positive, so it's going to be added to that, and you end up getting still negative 31.62. And then we could either do this, where we take this amount and multiply it by the 250 and add it to that, or we could go backwards from over here, the 36.73, and we end up finding that this is a negative 3.673 right there, right? Either or will get us the same place. Now, onto this guy over here. Let's see. We have RAZ, and RAZ is 543.9. So that's upwards. So, and it's negative. And then we have an additional 707. And I want to move this guy because he's going to be in my way. 2300, right? So he comes up. So we're going to add that 707 to this right here, and I get a negative 1251. Now I'm going to take this 2300, and it's going to come down, and it's going to be positive 1049, which you'd expect because it needs to equal that right here to go back to 0. So we're going to have, this is going to have this kind of a slope, and then this one's going to have more of a slope. All right, it's going to be a steeper slope because of that right there. And then this is just going to have the same slope all the way down because it's constant all the way along there. So if we take this and multiply by our 0.1, we get a negative 54.39. And then if we put in the contribution of this times that and add it to that, we end up with negative 367.1. And then we could either take this portion and add it to there after we multiply it to this, or we could take this and multiply by here and come over from the right. And if we do that, we get negative 104.9. Now here's our moments, and you can see this one way bigger than all the others, so it's going to be the, that's where the maximum is going to end up being. Right there, it just makes sense. So if we take the moments, we could say the moment at, I didn't label these, I think this is at B, is the square root of 59.54 squared plus 54.39 squared. Just to check, and we end up with 80.64 Newton meters. And then we could take MC, square root of 31.62 squared, but 367.1 squared, almost entirely going to be this. In fact, it doesn't really even change the results much. That's how much bigger this is than all the others. And then MD, square root of 3.673, that's just pathetic. And then, but also 104.9 squared, and we end up with 105. So this is the max by a large margin. So we already checked, already did that portion that I see right here. Now I have to decide key or tapered pin. And one of the reasons why I have to decide on that is they have different stress concentrations, but also their nominal stresses are quite different. Let's see, what am I looking for? I don't know. I think I want to find books and Shigley. Is it going to open up on this side or on that side? It opened up on that side. Okay, great. But I don't want you, I want to show you. So let's see if I drag you. Can I just let go right there while you open up? There you are. Okay, cool. All right, but it's the graphics are still trying to catch up. Okay, cool. So what we want to find here, we have the appendix. Boom. And stress concentrations. Boom. And if it's the tapered pin, therefore we would use for torsion, and use this guy. And I think I already did a problem like this though, so I don't really want to use the taper pin. Unfortunately, all my numbers are going to be jacked. Yeah, so I already did this one in an example, or maybe I did that as part of the solution. Did I already do the solution to this? No, I think I did this as an example. I'm not sure if I did the solution for this problem, for the homework yet. I sure hope I did. I think I did. I think I was trying to avoid doing something else, so I think I did it. But if we want to instead find the keyway, what we could do is we could come to this section right in here, and if you look just a few pages in, a couple pages in, more than that. All right. They talk about keyways a little bit. There's a stress concentrations to there. Did they ever show you the keyway? They have an ugly looking keyway. I don't like those keyways, but that's okay. This right here is where we're going to take our keyways from. So I'm not going to do the pins, so I'm going to adapt my problem, and that's okay. It'll make it closer to the homework solution. Come on, get over here. All right, so here are the torsion and bending stress concentrations for an end mill key seat, right there, of 214 in bending and 3.0 in torsion. So we're just going to go ahead and just use those. Missing values not readily available. By the way, though, those right there, that 2.14, as I mentioned before, if this thing will drag over this, 2.14 came from right around here, 2.14, like right in there. See it? And the other value, let's see, where's Shigley? 3.0. It came from pretty close to this one right here. I guess it says approximate values at the end of key with a torque transmitted by key of length of 2.5 D. Right? Some of these other parameters you're going to have to know to be able to get a better value of this. So that's why we're using sort of an approximation thing here. So we are going to use our regular stress calculations, stress formulas for the nominal stress, but just be aware, if we'd use the pin, they have their own little funky stress value to use along with it. So we're going to go with key. And then we're also, maybe we'll design this backwards and make the video longer than you'll probably want to watch it, but that's okay. For bending, the KT was approximately, now I forget, 2.14? I think that's right. And the KTS was 3.0 for shear, right, according to that Chapter 7 table. Let's get closer to reality. The bending stress is going to be MC over I. So we take our moment. Oh, and maybe we should find out what the I and J are going to be, right? It's pi over 64, and they said it was 30 millimeters, so 0.034. And I probably have it written down, but I'm too lazy. That's how lazy I am. I mean, it's pretty amazing how lazy I am. Few people are as lazy as that's not true. I don't think I have that kind of distinction, but I think I do have some amount of distinction. 3.976 E minus 8. These are meters, so I will take my 368.5 and my C of 0.03 divided by 2, divide by my I, 3.976 E minus 8, and I'll hit enter, enter, enter so I can use it again. 368.5 and 0.015, boom. I think I have 139.0 megapascals, tension and compression. Let me see, I didn't actually write those out. Yeah, well, I'm having different values. All right, so these are the nominal right there. So here's my TR over J. And this is at the center, right? So let's put some thought process into this. This is at the center. So to the left of this is the larger torque, to the right is the other torque. Now, if it had been like over here, maybe, we could only have used the torque that was next to it. We wouldn't have used the maximum torque. But the maximum torque's on this side and minimum torque on this side. So we're just going to go to the other side of this thing. And the torque that we found was 80 right there, right? And so you could just tell by the magnitudes, by the way, that the torque isn't going to be the driving thing. Although we do have a high stress concentration. So we have that 80 times our 0.03 divided by 2. And then we need our J, which is just 2 times I. And so just take 2 times that. And then take 80. Then 0.015 times it. And I say... oh, I didn't bother writing down what that value was. Let me write down what the value was. I jumped onto it, but let me write this down first. 15.09 was my torsional shear. But let me 2 times that. This was 7.952 E minus 8. 7.9. Sometimes I go too fast. All right. So anyway, if I wanted to get my max bending stress, that's just my KT times my nominal, or 2.14 times 139. 2.14 times 139, and I get 297.5 megapascals. And now I didn't leave enough room for the other guy. Well, we got more paper. what the hell? And so we go tau max, KTS, tau naught, or 3 times our 15.09. And 15.09, 3, we end up with 45.27 megapascals. All right. And so if we want our maximum shear stress theory, boom, 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 let's just based on our stress element that we'd have right here, we're predicting that somewhere near that that shear key is going to be this stress state. So for the maximum shear stress theory, we can do more circle. It doesn't hurt us at all. If I was going to do this one correctly, I think that means this guy would go down here and down here. And so there's going to be our R, and there's our C. And our C would be 297.5 divided by 2. Or let's see, so 297, yeah. So divided by 2, we get 148.7. And then so the radius, that's just that distance, so that's one of the legs, and the other leg is going to be the shear stress. So the shear stress is 45.27 squared. So the radius, flip them, I can even do this square that. I can put them together and it's like square root. And I think at 155.5, it looks like to me, megapascals. And so that's also not only the radius, but it's also the tau abs max, because it's right there. It's the radius of this thing. So the maximum shear stress theory, okay, well, we also, it's going to be the yield strength divided by 2 divided by the tau abs max. I think in the original problem, as we were looking this up here, we said something about being 304 stainless steel. So we could look that up in Shigley and in the back of the book. We have some stainless steel somewhere. Right there, 304 stainless steel, annealed. Only got one choice, but we have 276 is the metric yield strength. So somewhere 276 megapascals. So we'll say 276 divided by 2, I guess, divided 155.5, and I think we're going to get a bad result. 276, 2 divided, I think we're going to get 0.89. I'm not going to get more sig figs than that. We're predicting failure. Let's see what happens with distortion energy theory. Much easier to do once you get to this spot right here, because all you need is this equation right here, right? So you get the 297.5 squared plus 3 times our 45.27 squared, and take the square root of the whole thing. And we'll get a von Mises stress of 297.5 squared, 45.27 squared times 3, take the square root of the whole thing, and I get 307.7. So when I go to get my safety factor from distortion energy theory, take the yield strength divided by the von Mises, and I have 276 divided by 307.7. We could see where this is going. That's not going to be a pretty answer. We get 0.8, actually 0.90. Yeah. Still not good. So, is that where I ended this? That's where I ended this problem, but let's do a redesign. Or we could pick a different material, but let's say that we want to stick with that because we needed the stainless and we didn't have anything better than that. So let's say the design factor we're going to pick right here is our 1.5, right? So the allowable is going to be the yield strength divided by that. But that's going to be the distortion energy allowable, right? Right? So let's just do that, though. Let's just do the DET redesign because I'm tired. So we take 276 and divide it by 1.5. 276, 1.5, divide. And so we end up with 184.0 megapascals is our allowable. And in a previous video, I came up with the derivation, or I demonstrated the derivation. But we don't need to do it again. We have it written down somewhere. Mine are in my notes and in class. I don't know if it's 16 or 15 now. I think it's in class 15. No, this is class. Which class is this? Is class 18, isn't it? This is class 18, so I think it's in class 16. Yeah. Is it going to open it up? Does it know that I wanted to open it up? Or is it just going to go to right there? Why didn't it open it up? I don't know. I think it was in class 16. I think I talked about it in class 17 though. But here you go. I worked it all the way through, and it's somewhere down here somewhere. Oh, computer decided to be slow. What's up with that? Here's our redesign with maximum shear stress theory. And here's our redesign equation with distortion energy theory. So here is the big equation that we want to write down. So I'm going to write this down. Our D is equal to, oh, and I already did the, I didn't do the I did the allowable like within this thing right here. So we'll just pay attention to the fact that we had it there. So we got 4 times KT times the moment, and that whole thing squared, plus 3 times KTS torque squared. Right, let's square that and then take it to the 1/3. Right. And there's lots of that's kind of a long little do thing, so there's a lot of chances for us to make mistakes. It's also in metric, so there's a lot of more digits sometimes floating around. We get 16, 1.5 pi. Our yield strength is 276, but it's megapascal, so I'm an E6. Square root 4. My KT I said was 2.14. My maximum moment was 368.5 squared, and now I will take my stress concentration of 3. My torque was 80 squared, and then the whole thing to the 1/3. So Hewlett-Packard calculator to the rescue. I go 368.5, 2.14 times, square it, multiply by 4. And then 80 times 3 squared times 3. Add them together, take the square root, multiply it by 16, multiply it by 1.5, divide it by pi, divide by 276e6, divide. All right, so that's a big number. Then to take the 3, and I'm going to take the cube root of it. And what I'm left with makes no sense. Pooh! So I made a mistake somewhere. I hate that. It's a math mistake because I went too fast. Did I go too fast? How did I make the mistake? That's the big question. How did I make the mistake? This one looks really similar, doesn't it? 1, 3. Let's go ahead. Let's just go ahead and do it. Let's try it again. I see what I got. As I got 0.00. It's got a 3 millimeters. 3 millimeters. Don't accept 3 millimeters. Right? I see that all the time with students, by the way. But I won't judge this. 368.5. And we got 2.14 times that, and we're squaring. I got it squared. Multiply it by 4. Boom. Now we got 80 and times 3, and we're going to square it, and then we're going to multiply it by 3. We're good? Multiply it by 3. We're going to add those two together, take the square root of them. Gotcha. Going to multiply by 16. Going to multiply by 1.5. Going to divide by pi. And we're going to divide by 276 e to the 6 megapascals. Is everybody else? Yeah, okay. Divided. All right, so I get a pretty small, I get a number e to the 5. Now I'm going to raise it to the 1/3. And I get the same number. So how is that possible? Oh, that's actually 35. That's me not being able to read. All right, 35.61. That makes sense. We had 30 and it wasn't good enough, but 35 would be not quite enough. So we need to go to 40 millimeters. I don't think we should do 37.5. Maybe we could do 38. 38 might be one of our standard ones. Let's double check. And it might be, I mean, it sounds to me like 38 sounds like maybe a standard size. Let's look at A17 and see what they have in millimeters. 32, 35, 48. Nope. I mean 40, not 48. No 38 is what I mean. It goes 35 and then 40. So 40 millimeters is the correct redesign to use right there. The 40 millimeter shaft redesigned. Thank you. All right. How long is the video? An hour long. Wow. I got to go faster than that in class. No one's watching this video. Oh well. I must be taking like really long to talk lately.